On page 241 of the textbook, you will find problem number 34. Part A, find the open intervals on which the function is increasing and decreasing. Part B, identify the function's local and absolute extreme values, if any, saying where they occur. The function we're given, g of x equals x squared times the square root of 5 minus x. Well, the first thing I actually want to do is talk about the domain of this function. And what tips me off that I need to think about the domain is the square root, because I know this function will only be defined where the thing under the radical, under the even root, is bigger than or equal to 0. Adding x to both sides tells me that the domain of this function is simply the x's between minus infinity and 5. Well, that tells me that after I take a first derivative and I'm ready to look at a number line of signs, the largest thing I'll ever need to consider is 5, so I won't have a two-sided number line. I'll stop at 5. And in fact, when we get to 5 in our number line test, if we thought this went on forever, we'll probably find out we can't plug those values into the function to begin with, but it's always a good idea to remember the domain of a function. So now let's take a derivative. X squared times the square root of 5 minus x. I'm going to have to use the product rule. And I'm going to think of the square root as a 1/2 power. All right, so the product rule. The first times the derivative of the second plus the second times the derivative of the first. All right, so there's my first derivative. It's not really nice to work with right now. So let's see if I can make it look a little nicer for us. All right, so I've rewritten my negative exponent on the bottom of the fraction, and that should be a 1/2, not a 5 there. All right, and now I want to actually find a common denominator and see if I can make this even better to work with. At this point, I can probably tell that 5 would be a critical point if it weren't an endpoint. And then I need to set this equal to 0, and I could probably do that as is, but I feel like just making my first derivative easier to work with first. So let's find that common denominator. So I need to multiply the top and bottom of this fraction by 2 root 5 minus x. And when I do that, I'll get 4x times 5 minus x all over 2 square root of 5 minus x. And I'm going to go on and just rearrange this a little bit so I know everything's over this denominator. 2 times the square root of 5 minus x. And then on top, I have minus x squared. Distributing here, I'd have a positive 20x. And distributing one more time, I'd have a minus 4x squared. So minus x squared minus 4x squared would be minus 5x squared, and then my plus 20x. And I have my first derivative, and that's almost how I want to work with it. Let's see if we can do one more thing to make it a little easier to deal with. So just to remind us later on, our original function is this. And right now, we've worked with the first derivative until it's minus 5x squared plus 20x all over 2 times the square root of 5 minus x. On top, I have a common factor I can factor out of minus 5x. And I'll leave the bottom alone. All right, critical points would be any interior point of the domain where the first derivative was either equal to 0 or undefined. On top, there are two zeros, 0 and 4, so those will both be critical points. And 5 would be a critical point if it weren't an endpoint in the domain. The first thing we did was write down the domain of the function. So my critical points are just 0 and 4. And when I go to write down my first derivative number line, I know I don't need to go past 5. So not to scale, here's my number line I will use, and now I just need to summarize the signs in the first derivative. And so let's plug in some sample values. And I can imagine plugging in a -1. So on the bottom, when I plug in a -1, I'll get the square root of 6 times 2. And the bottom of that fraction, and I'm thinking about plugging in -1, the bottom of that fraction was positive. I don't really care what it is. It's 2 times the square root of 6, but it's definitely positive. If I plug a -1 in for x on the top, I'll have a -5 times a -1 times a -5. That's a negative times a negative times a negative would be a negative. And on this little part, my first derivative would be negative. Now we could do exactly what I did in the last example where we would grab our TI-83, we very carefully type in our derivative, and then we used a table to type in some values. But I like this kind of analysis where I just kind of think my way through it. Between 0 and 4, let's just use a +1. And again, on the bottom, I'll get out a positive, and in fact, plugging a 1 in there, I'll get out a +4. On the top, I'll have a -5 times a +1 times a -3 is a positive. And then finally, on this interval, I have to plug in something between 4 and 5, so 4.5 would be my go-to. On the bottom, I would have a positive. And on the top, 4.5 minus 4 is a positive. 4.5 itself is a positive, times a negative is a negative. Again, you can always actually plug the things in and evaluate them to numbers. You can also do this kind of analysis, but now I know what my function does. It decreases to 0, it increases to 4, and then it decreases to 5. What I'm thinking about is a function that basically behaves like this. It goes down to 0, up to 4, and then down again. Now, I know this function's not going to have these sharp places and it's going to be curving. I could look at my calculator, but that's just the idea I have in my head. And so I have a minimum of some kind here, a maximum of some kind here, and a minimum again here, right? Min, max, min. Let's plug these x values into our function to see what the minimums and maximums will really be. So I think this time I'll just build a little table here and then I'll write down my summary of everything at the end. Well, plugging in a 0 is easy. 0 times anything is 0. Plugging in a 5 will be easy because 0 times anything is 0. And then plugging in a 4. Let's see. 4 squared 16 times 1 is 16. Well, I was decreasing until x is 0 and then increasing, so that is a local min. I decreased from 4 to 5, so this is also a local min. So let's write that down. There are local minimums of 0 at x equals 0 and 5. There's a local minimum of 0 at x equals 0 and 5, and there's a local max of 16 at x equals 4. But now I know something else. I know that I decrease to 0, increase, and then decrease to exactly the same level before. If I look at that shape I'm thinking about, I go down, up, down, but I ended in the same spot. And so what I know now is that my function never goes below y equals 0. So that's not a local minimum. That's an absolute minimum because my function can never ever go past that. Still just a local max because that is the top peak there, but it comes down forever there. And maybe just to confirm this, we'll take a peek in our calculator. So let's type in x squared times the square root of 5 minus x. I'm going to hit zoom 6 to make sure we're all looking at the same viewing rectangle. And my function goes down to 0, up, and I can see that it's having a hard time on the calculator actually coming down to that value there. And that's just an artifact of the TI-83 having a little trouble. So what I think I'll do is I'll give you a better graph of this. I should zoom out anyway so we see that value at 16 way up there. There it is. And the function should be coming down and hitting the axis at 5. What I'll do is I'll post a better graph of this using GeoGebra, and you'll find that right below this video.